Good morning, everyone. Welcome to today's thru All Hands webinar. Today, our speaker is Susannah Dr. Susannah from PNL. Susannah is an expert in the science of aerosols and aerosol cloud-climate interactions. She has been leading the critical development and assessment of the aerosol process representation for thru, and we should see the significance of it shortly. And Susannah, so you take over.
Great, thank you for that introduction, Wu-Yin, and thank you to you and the other webinar organizers for the opportunity to speak. I'm happy. I think this is good timing to share some of the outcomes from the aerosol working group activity that I led. But before I start, I do want to emphasize that this was a team effort, and some of the key players are listed here on this slide. I won't read them in the interest of time, but it relied very much on critical contributions from multiple people. So moving directly to the talk, I first want to just introduce a concept that I'm going to refer to a lot for those who are not experts in this area. I'm going to be speaking about the impacts of the aerosols in the thru model on the aerosol effective radiative forcing. And so the effective radiative forcing is the difference in the net top of atmosphere radiative downward flux between two atmosphere simulations. And for the aerosol, we perform one simulation with present day aerosol emissions and one with pre-industrial emissions. And then we difference them using fixed sea surface temperature to ensure that the climate remains the same. And so this definition includes not only the immediate direct impact of the aerosols through radiation interactions, which is called ERF-ARI. It also includes the indirect effects of aerosols on clouds, which we call ERF-ACI, and that term and the overall effect additionally include adjustments to the aerosol forcing, which includes changes in the clouds, for example, in the cloud extent and liquid water path, as well as changes in temperatures, water vapor, and other aspects of the climate. So that's the terminology. And the reason why this is important and is an important metric for us to pay attention to is because the historical temperature record gives us a joint constraint on the response of the climate to greenhouse gas forcing, which we characterize through the equilibrium climate sensitivity or other measures of climate sensitivity. But it's constrained, the temperature record constrains the ECS jointly with the historical aerosol effective radiative forcing, since that also had a significant impact on the historical temperature. And because of this joint constraint, uncertainties in the and biases in the ERF for aerosol can impact not only our simulated historical temperature record, but also at a more fundamental level, our ability to constrain the uncertainty in future climate projections via the climate sensitivity. So that's shown here schematically in this paper from Watson, Paris, and Smith, where they emulated the response to of climate to these two terms, and they showed that if you select different ranges of values for the aerosol effective radiative forcing, it impacts the range of climate sensitivities that are consistent with the historical temperature. So the reason that we had a major effort focusing on this for EMV3 is that in EMV1 and V2, or thru V1 and V2, we had a problem where the temperature in the mid-20th century was significantly lower than it should be, even lower than in the pre-industrial. And through single forcing experiments, Chris Golas identified that this could be addressed through reducing the effective aerosol radiative forcing to an estimated range of minus 0.5 to minus 0.7 watts per meter squared. And so this was the target range that we were asked to achieve. So I'm giving away the punchline right away, which is that we did achieve that range, or it got kind of up to the upper end of it in V3. So this slide is summarizing the evolution from ETHRIS-1 V1 and V2 to V2 and V3, also broken down into the direct and indirect, or ERF-ARI and ERF-ACI, as compared to the multi-model ranges. And you can see that the overall aerosol effect from V1 was kind of on the edge of what the community assessments think is reasonable based on multiple lines of evidence, but V2 was actually right in the middle of that range and still had this problem with the historical temperature record. And in V3, with this significant reduction, we do get improved agreement with historical temperature, as I'll show later. So I want to share a bit about how we achieved that, and also some of the thought that went into it. One thing that we did think about at the beginning is whether the problem of the cold temperature might be due not necessarily to the aerosol forcing, but to the overall climate response to the aerosol forcing. And one way of measuring that would be if the climate in E3SM had an unusually strong aerosol efficacy, so an unusually strong response to aerosol relative to its response to greenhouse gases. And so we performed a more apples-to-apples calculation of that compared to what had been done before, and then benchmarked it against a recent model intercomparison study. And so we did find, with a more apples-to-apples calculation of the efficacy, that it was a bit higher than what had been calculated in Chris's paper, but still within the range of other models and not really an outlier. So we determined that that was probably not the main issue. Then another issue that we looked at, and that we knew actually going into this was a problem, was that we had an excessive aerosol burden. And so this is a slide showing that the sulfate aerosol, one of the key anthropogenic species, had increased significantly between V1 and V2. Kai has done some careful analysis to track this down to changes in the convection and turbulence tunings that impacted the aerosol burden, causing this change between those two particular model versions. So in some of the early development efforts led by Ji Wen and Yun Peng, after introducing new microphysical schemes, they ended up with an extremely strong aerosol indirect forcing. But by introducing improvements to the wet removal, they were able to reduce the biases in the aerosol burden, and thereby also reduce the aerosol indirect forcing and the direct forcing as well. This led to an improvement in the aerosol burden, but it didn't have a very strong net effect on the aerosol effective radiative forcing because of offsetting effects in the direct and indirect effects. This is another slide also showing the impacts of the wet removal a little bit more clearly, partitioned out into the direct and indirect effects. So the top panel here is the total ERF air and its geographic distribution. At the left, for a case, and these are kind of from an intermediate development version of E3SM from last year in the summer. The left-hand case is showing a version with a lower bound on the cloud droplet number concentration of 20. The middle case is showing the removal of that lower bound and what the impacts of that are on ERF air, and the right-hand side is showing the impacts of the wet removal. And so I want to kind of point out here that this NC20, so the lower bound on droplet number concentration, has a very large effect on ERF air, and I'll talk a little bit more about that later. And that effect comes almost entirely through the indirect effect, whereas the wet removal has limited impact on ERF air, but it does have significant impacts on both the direct and indirect effect that offset each other. So another thing that we looked at then as well was the partitioning of the aerosol effective radiative forcing into three mechanistic components: the Twomey effect, which is the direct effect of cloud brightening due to having more cloud droplets, and the effect of changes, and which we call adjustments, to the liquid water path and to the cloud fraction. These calculations were done by Johannes, and they compare version 2, version 3, and a number of models from previous model intercomparisons, as well as the community-assessed ranges from Belwan et al. And you can see that E3SM v2 and these candidate versions of v3 that were assessed are all well within the range of other models. They do have the opposite sign of liquid water path adjustment that the Belwan assessment suggests, but the other models do as well. So this led us to conclude that the warm cloud processes per se were not significantly different from other models, and likely not a cause of our different behaviors in E3SM. We also looked at the historical evolution of aerosols from anthropogenic sources that are coming in through files, emission files from input permits, to verify that they appear reasonable, that we don't have any significant issues in either the emissions or some process controlling the historical evolution. So this example is showing a comparison against ice core data from Mosaid et al. And E3SM is shown in red, and you can see that E3SM falls well within the envelope of the CMIP6 models, which is the shaded gray area. All of these are higher than the ice core data in most cases, and this is thought to be due to the fact that the ice core data are collected on mountaintops where the model doesn't resolve the topography as well to kind of clearly to correctly get the lower concentrations at those altitudes, but the overall shape of the time series appears to be pretty reasonable compared to the ice core data. So we concluded from this, and also from examining the dry deposition equations in the model, that we didn't have any clearly identifiable problems with either our historical evolution or with the dry deposition, which was identified as a problem in the UK ESM model, but not in our model. So that was a kind of quick tour of some of the different hypotheses that we looked at. And now I want to show you at the end, this is a preliminary assessment of the breakdown for the changes that we did end up making. What were they, and how did each of these changes impact the aerosol effective radiative forcing? And this is this table will eventually appear in the atmosphere overview paper, and may have some updates by then. So I do want to emphasize this is preliminary, but we were able to attribute some of the changes based on sensitivity tests that have been done so far, either using the final version of v3 or a near final version. And we find that one of the two largest single parameter perturbations that impacted ERF were an increase of the minimum droplet limiter, which is a prescribed lower bound on droplet number concentration from 10 per cc in V2 to 20 per cc. This is the single largest impact, and it explains on its own 40% of the total change in aerosol ERF from version 2 to version 3. And additionally, we doubled the DMS concentrations and therefore the DMS flux into the atmosphere. This is a major natural background source of aerosol and cloud condensation nuclei, particularly in remote ocean regions. And this is known to impact ERF in other models. And that, in fact, turned out to be the second largest single parameter change in impacting ERF. In addition to that, we retuned the auto-conversion ND exponent to weaken the cloud response to aerosol. We also made several changes that reduce the lifetime of aerosols in the atmosphere in order to improve the aerosol burdens, which had been increased previously as a result of retunings elsewhere in the model. And so the net effect of those changes is also fairly significant. I do want to also mention that there are a couple of changes that were significant developments to the model that impacted ERF. So those include the updates from MG2 to P3 led by Ji-Wen Fan, the inclusion of the convective microphysics as well, and the impacts of several new aerosol features. The changes in the microphysics have, so Yun Peng's paper published earlier this year shows that they significantly offset each other, and hopefully we can quantify those as well for version 3. And the new aerosol features mostly have minor impacts on the overall ERF air, but the new SOA feature does have some impacts on the direct and indirect effects that largely offset each other. So I want to talk a little bit more, since the two largest single parameter changes impacting ERF are the minimum droplet number limiter and the increase to background DMS, so background CCN. I want to talk a little bit more about why it is that increasing the background ND weakens ERF ACI. So this is actually a pretty well-known result in the aerosol climate modeling community. The figure I'm showing here is from a Nature paper by Karsla et al. In 2013 that schematically explains the mechanism by which this is understood to happen. And it results from several physical saturation effects in the causal chain of processes that connect anthropogenic emissions to the aerosol effective radiative forcing. The first of those is related to saturation in the formation of aerosols and therefore CCN from gaseous precursors. When vapor concentrations are very high, the addition of more vapors leads to increasingly smaller increases in CCN. There's a similar and fairly pronounced saturation effect in the activation of CCN to forming cloud droplets in regimes where there are very high concentrations of CCN, and particularly particularly when those clouds have relatively lower updraft velocities and aren't able to generate high supersaturations. The third is an increase in cloud albedo with increased cloud droplet number, of course, also saturates at some point. So this is the Twomey effect, because you can only reach a maximum albedo of 1. At some point, the cloud can't be made any brighter. And so the net effect of these processes all saturating the impacts of aerosol on the effective radiative forcing is that at very low background aerosol concentrations, introducing additional aerosol has a significantly stronger effect on the total cloud albedo and the effective radiative forcing compared to introducing the same number of anthropogenic aerosol into a climate where the background aerosol concentrations are significantly higher. So the bottom right panel is illustrating that very high sensitivity at low background as compared to much lower sensitivity at high background. And so this explains why the impacts of increasing background ND are so large. And I want to show a few early results from the paper I'm leading that's going to delve into these two sensitivities in a bit more detail, showing that if we scale the DMS emissions between 0 and 8, we can reproduce this kind of sublinear curve that was schematically shown on the previous slide in the ERF ACI response. And the shape of that curve, it remains the same as we change minimum CDNC, but the base level of it increases as we increase the prescribed background droplet number. And I'm now superimposing on top of that where version 1, version 2, and version 3 of EAM fall on this chart. And so the colors are matching the values of the minimum ND limiter. And so you can see that from V3 to V2, had we only changed the minimum droplet number limiter, we would have moved from this purple star to this blue dot, and the actual location of V2 is the blue star. So you can see we immediately that had we done nothing else but increase the background ND from 10 to 20, we would have gotten the majority of the response. So this is kind of disheartening because on the one hand, we have significant enhancements in the aerosol and cloud processes in version 3 that should, definitely be appreciated and will add a lot of value to the types of use cases that this model can be used for by the community. On the other hand, it would be preferable if we could have identified a way before finalizing the model to reduce to improve the simulation of the historical temperature record without needing to use this kind of unphysical lower bound. So I think one of the things that this points to is that we need to do more work to really elucidate and address both the structural causes of low ND in the model that result in the model having such a strong sensitivity to this lower bound, because we see that low values of ND appear to be occurring more frequently in the model than they do in reality. And also more work on background pre-industrial aerosol sources, not necessarily just oceanic DMS. This was the one that was easiest for us to address on a short time frame. So I have a little bit more to share on this. So we were able to also partition out these effects in the scaling experiments into the direct Twomey effect, the cloud fraction adjustment, and the liquid water path adjustment. This is the same partitioning method I showed before. And you can see really clearly that the effect is almost entirely coming, in this case, from the direct ACI effect, the Twomey effect. The cloud fraction adjustment is fairly poorly constrained by the community assessments and other models. So every single value of it is within the accepted range. And the liquid water path adjustment remains inconsistent with the Bell-1 range, but consistent with other models across the entire range of scalings. We are also working with Christina McCluskey at NCAR and Ching Niu at University of Oklahoma to compare against in situ observations of aerosol and cloud condensation nuclei from the Socrates field experiment in the Southern Ocean. So these include vertical profiles of aerosol in the accumulation mode and the course mode, and we are doing pretty well in E3SM on simulating both of those. And the increase in DMS emissions improves our agreement with the accumulation mode aerosol, while, as expected, having almost no impact on the course mode aerosol. So this is really encouraging in that it suggests that, at least for the boundary layer, our increased DMS is improving, maybe improving our agreement with the aerosol forcing for the right reasons, because there's improved agreement with actually observed aerosol concentrations. So there's more to come on this, but that's a taste of what we're looking at with in situ measurements. I also want to share another comparison with in situ measurements, this one also comparing the impacts of DMS scaling. So this is from ground-based networks in continental regions, and was prepared by Ming-Xuan Wu. And in this case, you can see that there's almost no impact of the DMS scaling. So the red, blue, and green dots are almost identical in location. This is not surprising, but it kind of illustrates the point that it's really critical that when we're doing this kind of diagnosis of problems in the model, that we clearly identify our hypotheses about what physical mechanisms are causing them, and then make sure that we include metrics and benchmarks and diagnostics that are relevant to those particular mechanisms. So this diagnostic would be relevant and is relevant for other mechanisms that are impacting aerosol concentrations in the model. It's very valuable, but it doesn't shed light in this particular case. So after all of that work, I do want to show finally the improved agreement with the historical temperature records from that resulted from all of these changes. So you can see the green line here falls really beautifully on the black line. So in the end, we did see that reducing the aerosol forcing in our model did result in better agreement with historical temperature. I do want to emphasize that that doesn't necessarily imply that the value of the aerosol effective radiative forcing in our model is the correct value, because of course there are many other factors influencing the temperature evolution, but having a model that can simulate historical temperature evolution is very important for us to be able to use that model with confidence for future climate projections. And there may be multiple model variants that can produce such a record, but it is kind of a minimum requirement that we need in order to be able to really think about future projection scenarios with this model. In addition to improving the global mean temperature, we also improved agreement with the historical temperature gradient. So I want to mention that as well. So yeah, I think I'm out of time. So I had just a couple more slides, but I'll just skip to the end here and just share a couple of quick lessons learned, that some of which I've mentioned earlier. For other bias reduction efforts, I think it was really critical that we had a team that brought together multiple perspectives on the issues, including from the cloud side, the aerosol side, and aerosol cloud interactions expertise and expertise on diagnostics, and that this was coordinated through a central point of contact. I think that I do think that was really critical to success here. And I think also having a clear definition of the goal with objective metrics and then coordination across other groups with the coupled group and the V3 atmosphere integration team was important as well. In addition, having very clear bias hypotheses to explain what was causing the biases in the aerosols and effective forcing that we saw, and having robust tools and workflows ready to go so that we could quickly turn around results and analyses for sensitivity cases and iterate rapidly was critical as well. And then finally, again, our results point in part to the fact that that more work is needed to improve understanding and representation of background aerosols and the structural causes of low ND. So that is what I have to share, and I am happy to take questions.